For video 4 on limits, this one we're just going to do a proof that a limit doesn't exist. So the simplest one with that is just to take the alternating sequence that alternates between plus and minus 1. But before we go to proving that this doesn't have a limit, we have to talk about what it means for a limit to not exist. So hopefully we're getting a little bit more comfortable with these quantifiers and the definition of a limit. But recall that we say that a sequence AN has a limit if there's some number L, which is the limit. And the point is that no matter how close we want our sequence to be to the limit, so for every epsilon, there's some point in time after which, and forever after which, every n greater than capital N, then the distance between our sequence point and our limit is going to be within that threshold of epsilon. And so we've seen, I think there are 3 videos so far where we go through proofs of this stuff. I might make more in the future. But if we want to negate this, right, if AN doesn't have a limit, well, our intuition should be that that means there isn't an L that works. So in other words, no matter what L we choose, we're going to break this. And so if we think about that, it means that no matter what L we choose, there's got to be some epsilon that doesn't work. And that epsilon doesn't work because no matter what n we choose, no matter how big of a number we get, we can still find some number bigger than it, such that this inequality breaks. So there's a lot going on there, so I'm going to just write down what we have. But basically, to negate a statement with quantifiers, we have to flip every quantifier. So we change there exists to for all. So you see I've done that everywhere, like for all exists, exists for all, and exists, etc. And then at the end, the sort of the punchline of all of this stuff is just that, oh, the distance between AN and L was small, and now in this one we want the distance to be big, right? So this is what it means for AN to not have a limit. And let's do some examples. Right? So I've reprinted that here. So here's our sequence. It alternates between 1 and minus 1. And the reason why can't the limit be 1? Well, if L were equal to 1, then if 1 is not a limit, then that means there's some epsilon that we can't sort of stay within that distance of. Right? And so why can't the limit be 1? Well, every other term, the distance between our supposed limit 1 and those negative ones, that distance is 2. So if we took epsilon to be, I don't know, 1/2, then we're not going to stay within 1/2 of 1, because every other term we're going to be 2 units away. Why can't the limit be minus 1? Well, the same reason. Every other term will be 2 units away from it. Why can't the limit be 1/2? Well, basically every term we're either 1.5 away from it, or we're 1/2 away from it. So we'll never be within, say, 1/10 of it. And 5, well, 5, yeah, I mean, we're never even really close to 5, right? We're always at least 4 away from it. And so as a warm-up, let's write a rigorous proof that 1 is not the limit of this sequence. So to show that 1 is not a limit of minus 1 to the n, we need to show that basically there's some threshold that doesn't work. And we just sort of talked through that. And so let's take epsilon equals 1. So no matter how big my natural number n is, there will always be some odd number bigger than it. And then if I look at that, if I take that little n, then a sub n is going to be minus 1. And then the distance between minus 1 and 1 is 2. So the distance between an and my limit, well, that's minus 1, here it is, and 1. That's going to be distance 2. And that's not going to be smaller than epsilon, because we could have picked epsilon to be like 1/10 if we wanted, but even epsilon equals 1 doesn't work. Right? So 1 is not a limit because we can't get within 1 of that limit forever. Right? So now let's show that no number L is the limit of AN. And to do that, we have to sort of do 2 cases. But the point is that L can't, that's supposed to be a minus 1. yeah, this is supposed to be a minus 1. So either L is not 1 or it's not equal to minus 1. It could be both. And so we'll do the case that L is not equal to 1. So I've drawn a picture, and the picture L is to the left, but it could be to the right. And what I've done is I've defined this distance d to be the distance between 1 and L. Right? So it's the absolute value of 1 minus L. And what I'm going to do is I'm going to define this epsilon to be d over 10. So it's going to be this tiny range here. And the point is we're going to let epsilon, this says epsilon, it should say equals. I'm really sorry about this slide. This should say epsilon equals delta over 10, or d over 10. And so the idea is that, the sequence is alternating between plus and minus 1. And so whenever the sequence is equal to 1, its distance to our limit is going to be d. And so it's not going to be smaller than d over 10. And so we'll show the sequence never stays within epsilon of L. And so we just finish it. So for every n in the integers, in the natural numbers, we can find an even number bigger than it. And then when we compute the term, a sub n is going to be 1. And so when we compute this difference, a sub n minus L, well, that's 1 minus L, which we call d. That's this picture up here. And that's going to be definitely bigger than delta over 10, which is what we said equal to epsilon. Again, this really should be an equal sign. And that's a contradiction, right? In other words, we found an epsilon that we can't, stay smaller than. Right? So this is one of the harder things to do, is to show that a limit doesn't exist. But I invite you to review this video a few times, or we could talk about it next week in class. Thank you.